Okay, let us see what we have done so far. A was a matrix of the size n cross m. It was mapping R m to R n. This we have seen. We have seen all this. Then we have also seen that A transpose A. We have seen many things. I am only narrating a few which we did in the towards the end of previous class, because I cannot go on narrating all the properties. A transpose A and A transpose, they have the same distinct eigenvalues. So, 0, I am keeping a provision of 0. In fact, I would call it lambda 0, lambda 1 dot dot say lambda r, and lambda 0 could be 0. Corresponding eigen subspaces w lambda 0, which I denote as w 0, and in general if it is lambda I, this is w lambda I. These are eigen subspaces. Okay. That is subspaces for A transpose A. Okay. For A transpose A, it takes a vector from this R n cross A cross m. The eigenvector also is here. Okay. So, corresponding eigen subspace also is here. So, this belongs to, this is all, these subspaces are part of R n or R m, and our notation was w lambda 0 prime dot 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 w lambda r prime. These are eigen subspaces for A transpose. These are contained in R n. Okay. And what we have seen, we have shown that their eigenvalues are same. The distinct eigenvalues are same both for A transpose and A transpose, and not only that, we are showing actually that if you consider say lambda 1 to lambda r, okay, that is non-zero eigenvalues. Consider any w lambda I, that is I equal to 1 to r, okay, and consider the corresponding w lambda I prime. Then both have same dimension, which means for any non-zero eigenvalue lambda I, the multiplicity is same whether it is an eigenvalue for A transpose A or A transpose. The two dimensions are same. That is what we are trying to prove last time, and that is where we stopped. Okay. So, maybe we take it up now. That suppose I consider lambda I, a particular lambda I not equal to 0, w lambda I, say find out a basis, say u 1 dot 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 u n I basis of this. Okay. But they are also eigenvectors, because they belong to w lambda I, eigenvectors with eigenvalue lambda I. Okay. Then we have seen that A u 1 dot 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 A u n I, they all belong to, because they are all then eigenvectors of A transpose with the same eigenvalue lambda I. That means, they all belong to w lambda I prime, because if u 1 to u n I, they are the eigenvectors of A transpose A with eigenvalue lambda I, then A u 1 to A u n I, they are the eigenvectors of A transpose, but with the same eigenvalue lambda I. So, they belong here. In fact, last time we proved, and let me prove it again, that this if u1 to u(n)i they are linearly independent, in fact they are, because they form a basis, then au1 to au(n)i they also are linearly independent, which is easy to prove. Let us suppose I form a combination like this, I equal to 1 to n(i) and equated to 0, you can easily write it as a c I u I equated to 0. That means this vector belongs to null space of A. Okay. This vector belongs to the null space of A, and null space of A is same as null space of A transpose A. We have seen it already. Now, null space of A is same as null space of A transpose A, which is also same as the eigen subspace with 0 eigenvalue, there is W 0. Okay. But since lambda I not equal to 0, we have W lambda I intersection with W 0 is only 0, because lambda is non-zero, and we already know that eigenvectors belonging to different distinct eigenvalues are linearly independent of the respective subspaces. They are mutually disjoint, they only intersect at origin, that is at 0. Since lambda u was taken to be non-zero, this is 0, and look at this vector summation C I u I. Since each u I belongs to W lambda I, this summation belongs to W lambda I, but at the same time, since A times this summation is 0, this also belongs to W 0. Okay. That is, this belongs to this, also this belongs to W lambda I. That means, this belongs to the intersection between W 0 and W lambda I, but that is only 0, which means this vector has to be nothing else but this 0 vector. And u1 to a1i they were linearly independent, this only implies C I equal to 0. That means, au1 to auni they are also linearly independent. Question is, do they span this entire space? They of course span a subspace of W lambda I prime, and the dimension of the subspace is n(i). But if they also span the entire W lambda I prime, then I can easily say that W lambda I prime has the dimension n(i), which is same as the dimension of W lambda I, which means multiplicity of lambda I both for A transpose A and both for A transpose are same. So, I have to see whether these vectors a u1 to a uni they span the entire subspace W lambda I prime or not. So, to see that, let us take any vector belonging to W lambda I prime, we will see whether it can be written as a linear combination of this n(i) number of vectors. So, let us take a vector say W prime belonging to W lambda I prime. If W prime is here, it is an eigenvector of A transpose, it is an eigenvector of A transpose with eigenvalue lambda I, that is A transpose W prime is lambda I W prime, is not it? This means that W prime actually is an eigenvector of A transpose, that is why it is in the eigen subspace. Okay, that is these two things are equivalent. The W prime belongs to W, this eigen subspace means the operator A transpose has W prime as one of the eigenvector with the eigenvalue lambda I. But we have also seen that if W prime is an eigenvector of A transpose, then A transpose W prime which belongs to W lambda I, meaning A transpose W prime is an eigenvector of A transpose A with eigenvalue. These are all done in the class previously. Eigenvalue, same eigenvalue lambda I. So, this means if you pick up any vector W prime belonging to this eigen subspace W lambda I prime and apply the operator A transpose over it, what you get is a member of W lambda I, and therefore, it can be written as a linear combination of u1 to uni, is not it, because they form a basis of W lambda I. This means I can write A transpose W prime as some kind of linear combination d I, those vectors u I equal to 1 to say n I, because this belongs to W lambda I. If it be so, and now if I apply A over this, and therefore, A over this, and A can be brought here, A can be brought here, what do I get? On the left hand side, I get this W prime. My starting assumption was, you see, A transpose W prime was lambda I W prime. So, lambda I W prime is equal to d I A u I. Important thing is lambda I not equal to 0. This is very important, and therefore, I can take out lambda I from here, this, which means any vector W prime belonging to this eigen subspace can be written as a linear combination of this A u 1 to A u n I as shown here. So, that means these linearly independent vectors form a basis of W lambda I prime, which means W lambda I prime also has dimension n I. Okay, that means both the subspaces have the same dimension, or lambda I has the same multiplicity n I, whether it is for A transpose A or for A transpose. So, that is proved. Mind you, only it is true for those subspaces for which lambda I was not equal to 0, because then I say I could do here, I could say here, I could prove that they are linearly independent by saying that, I mean, intersection between the two subspaces is 0. Okay. This I could make a use of only when W lambda I was different from W 0 and intersection was 0. Okay. And when it comes to the special case lambda 0, which is actually 0, that time you can easily see, on one hand you have got W 0, another hand you have got W 0 prime, but both have the same dimension, both have the same, both have the yes. Because okay, maybe I come back to this issue little later, this is not relevant here. So, lambda W 0 I leave aside. Okay. Now, one more thing, consider these matrices A transpose A, also A transpose, they are all Hermitian matrices, symmetric, in this case real symmetric matrices, but in general Hermitian matrices, and not only that, they are non-negative definite matrices we have seen. So, their eigenvalues are real and either 0, or if not 0, they are strictly positive, this we know. Further, we had seen further, if eigenvalues are 0 and then lambda I equal to 1 dot dot say r, lambda 1 not equal to lambda 2 dot dot, these are the distinct eigenvalues, and in this case we also know they are all greater than 0, because it is non-negative. Suppose this is given, then we had made use of one property throughout this course, adaptive signal processing course, that these matrices, Hermitian matrices, are actually any Hermitian matrix, and this is a special kind of Hermitian matrix, they are diagonalizable. Okay, and that is why we could diagonalize them, and there we know that eigenvectors belonging to distinct eigenvalues, they are orthogonal. That is not a problem, that we have proved, but we have further assumed that they are diagonalizable. We made use of it in this course. We did not prove it actually, we might prove it maybe towards the end of this class. But the fact that I am going to stay is this: what is the space on which A transpose A works? The vector space is R M. R M is actually can be written as, because it is Hermitian, R M can be written as W 0 direct sum W lambda 1 direct sum dot 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 direct sum W lambda R, and the other one A transpose is works in W R A. Okay, it works on R n W 0. Okay. Okay, this we can prove, and this means these operators are A transpose is diagonalizable, that is you can find out a set of in fact case of linearly independent vectors. Why even linearly independent? You can make them orthonormal, you can take a set of orthonormal vector eigenvectors or basis vectors for W 0, for W lambda 1, for W lambda 2, and when you append them, this forms an orthogonal or orthonormal basis for this. Okay, and using them we can diagonalize the matrix. Okay. We have seen it already in the class, but how this is true we did not prove. We make use of this result, that this vector space is diagonalizable, okay, because if the space is can be written like this, we have seen it already 2-3 lectures back, that if the vector space can be written like this, that is the disjoint sum of there is direct sum of eigen subspaces corresponding to the distinct eigenvalues, then it is diagonalizable. Why diagonalizable? That also we have seen. How to diagonalize the matrix operator, that also we have seen. Okay, so that thing applies here. But why it is so? That is why it is that if the operator is Hermitian, the corresponding vector space can indeed be written like that, and therefore the operator is diagonalizable. That we have not proved, but without saying all this, we have made use of this fact in this course. But I thought maybe it will be proper to give a proof toward the end of this adaptive signal processing course, which I will do little later. But let me make use of this fact. This means one more thing, you see, w lambda 1, w lambda 1 prime both have the same eigenvalue lambda 1 and same dimension, maybe n 1, w lambda 2, w lambda 2 prime both have the same dimension, maybe n 2, and same eigenvalue lambda 2. So, for w lambda prime and all that, but overall dimension here is n, overall dimension here is m. So, w 0 has dimension which is m minus within bracket n 1 plus n 2 plus dot dot plus n r, w 0 prime has dimension here as n minus again n 1 plus n 2 plus dot dot n r. So, the dimension of these two spaces are not same, w 0 and w 0 prime, but these are the null spaces we have seen, these are the range spaces of that operator. Okay. These are the things we have. If this be the case, and one more property we see, one more property, this is one thing we are assuming, we have not proved, we will prove, subject to that we accept that using this eigen subspaces R m and R n can be written like that, which means they are diagonalizable, we know. And second thing, another property before we go into the SVD representation is that suppose you take u v belonging to w lambda I, and u not equal to 0, v not equal to 0, but u is orthogonal to v, meaning u Hermitian v is equal to 0. Okay, inner product is 0. Suppose it is given u and v both belong to they are just two non-zero mutually orthogonal vectors, okay, belonging to w lambda I. Then we know a u and a v, they also belong to w lambda I prime. That is the eigen subspace for a transpose with the same eigenvalue lambda I. Question is, are these also orthogonal? We can see if you take a u Hermitian a v, what do you get? U Hermitian, and now Hermitian in this case will be simple transpose, because we are dealing with all real cases only, a transpose a v, but a transpose a is the operator, v is taken from w lambda I. So, v is an eigenvector of a transpose a. So, that means you will simply get lambda I times u h and v, and u h v is 0. So, 0. So, that means if two mutually orthogonal vectors are taken up and they are mapped to w lambda I prime by this operator a, they also remain mutually orthogonal, which is a very interesting result. It means that and this is true not only for lambda I greater than 0, this is true for any lambda I. So, that means if you take up for one orthogonal basis for each of these w lambda 1 or w lambda 2 and map the basis vectors by using this multiplication by a, you get another orthogonal basis for the respective vectors, for the respective eigen subspace like w lambda 1 prime, w lambda 2 prime, which means this a operator maps one orthogonal basis of w lambda 1 to another orthogonal basis of w lambda 1 prime. So, same for w lambda 2 to w lambda 2 prime dot 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 dot, or w 0 to w 0 prime. Okay. So, one orthogonal basis of one eigen subspace is mapped to another orthogonal basis of the corresponding subspace eigen subspace with the same eigenvalue. Okay. This is another interesting property, and instead of taking this, suppose u is such that norm of u, norm square of u or norm of u, that is u h u, suppose it is 1, that is its unit norm. And if I take a u, is it also unit norm? Answer is no. If you take this norm square, this is u h a transpose, in fact all h should be transpose according to me, because we are dealing with real cases, a u, and a transpose a u, is an eigenvector because u belongs to w lambda I. So, a transpose a u is simply lambda I times u transpose u, but u transpose u or u h u, you can put it transpose also, that is 1. So, this is lambda I, and lambda is, if I am taking this lambda I from this place at lambda is greater than equal to 0, you can call it sigma I square. Okay. So, that means if you take, so that means if you take u as a unit norm vector and map it to u as a unit norm vector from w lambda I and map it to w lambda I prime by multiplying by a, that a u vector is not unit norm, its norm is lambda I or sigma I square. Sigma is called actually sigma singular value. Now, we come to this thing, the main SVT decomposition theorem, but while in this journey we have proved a lot of things, which for your benefit. I mean, we could have skipped, but I wanted to get into those mathematical details because they come every now and then in our, any kind of discourse on statistical signal processing or adaptive signal processing and those kind of things. So, that is why I have included some proofs and also for completeness, because I did not want to leave anything unproved and use those results, that is not my habit. So, that is why I am proving everything. So, now let us come to SVT theorem. We will assume the same A matrix on all those, I am not rewriting them. Suppose so we are assuming same A matrix n cross M and all those notations, everything continuing. So, even if I write SVT theorem, I am not bringing any new notation or notions. Okay. Now, suppose A is a given matrix and I am considering say w lambda I am taking to be greater than 0, not equal to 0. Okay. Or maybe it is not required, I am taking just lambda I, w lambda I. From w lambda I form a set of orthogonal basis vectors using the same notations. Okay. And each of them has unit norm. This is orthonormal, basis. Okay. This is an orthonormal basis vector, basis set, this is given to me. So, if I use A matrix, multiply each of them, pre-multiply, I will get an orthonormal basis for w lambda I prime that you have seen, but they are, that will be orthogonal, but their norms of each vector will not be 1, but will be equal to lambda I or sigma I square. So, that means if I choose say beta I 1 as simply A times alpha I 1, but divided by square root lambda I, positive square root lambda I, which is sigma 1, in this case sigma I, because I is eigenvalue, dot beta I n I is nothing but I am doing the same multiplication, but to make them unit norm I am dividing them by sigma I, because we have seen that if you multiply them by A, they maintain orthogonality, but unit norm is lost. So, you have to divide by the corresponding singular value or square root, positive square root of corresponding eigenvalue lambda I, which I denote by sigma I. So, then they become unit norm, and in this case this forms not only orthogonal, orthonormal basis of w lambda I prime. Okay. Now, suppose I form a matrix like this, A times, suppose I put like this, I first start with eigenvalue 1, not 0, eigenvalue 1, I will order like this, eigenvalue 1, then eigenvalue 2, dot eigenvalue r, that eigenvalue 0 case will be taken up at the last. So, first consider w lambda 1 corresponding orthogonal basis vectors you write alpha 1 1 dot alpha 1 n 1, then take say alpha 2 1 dot alpha 2 n 2 dot dot dot, say you take alpha r, rth eigenvalue, that is for w lambda r 1 dot 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 alpha r. Thus, I am just doing nothing, I am just putting the orthogonal basis vectors side by side. So, they are not only mutually orthogonal, since the eigenvectors corresponding to distinct eigenvalues are orthogonal by themselves, this interset is an orthogonal basis vectors, okay, because alpha 1 to alpha 1 1 to alpha 1 n 1, they are not only mutually orthogonal, they are orthogonal to alpha 2 1 to alpha 2 n 2, because the corresponding eigenvalues are distinct, so on and so forth. So, I go from 1 to r and then I write alpha 0, that is the 0th case, it is just an ordering, there is nothing much in it, that is the 0th case I want to separate out right at the last, alpha 0 n 0. Okay. And essential thing is how many eigenvectors how many such vectors I find, same as the dimension of the space R m, because of this result that R m was, I mean, can be written like this, A transpose S is diagonalizable, that means R m can be written like this. So, if you take all the orthogonal basis vectors of the respective subspaces, append them, total you get must be equal to m, that is the dimension. Okay. So, that means this is how many m, total m. You can call these vectors, maybe you know, I mean you can give it a name. Now, let me see what name to give. Maybe you can call it sigma. If you do this A sigma, what will you get is A times this or A times this will be simply by my definition sigma 1 times beta 1 1, sigma 1 times beta 1 n 1, like that. Okay. So, if I form another vector, another matrix beta, first like here eigenvalue 1, here also eigenvalue 1 1 dot dot dot, say beta 1 n 1, then again beta 2 1 dot 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 beta 2 n 2 dot 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 beta r 1 dot 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 beta r in r, that should have been in r here. And then I take vectors corresponding to 0 eigenvalue beta 0 1 dot 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 beta 0, it will not be n 0, because I told you for non-zero eigenvalues the multiplicity is same, but for the 0 eigenvalue it is not. So, you can give it any name n 0 prime. You form a matrix, this is again an orthogonal matrix, because I mean first within each eigen subspace vectors are mutually orthogonal, that is how that we have seen, because I mean that is what I have seen, that if alpha 1 to alpha n 1 they are mutually orthogonal, A times them also will be mutually orthogonal, then orthogonal, and since they correspond to defined eigenvalues, okay, I mean these sets also, I mean whether you pick up somebody with eigenvalue 1 or somebody with eigenvalue 2, they also will be mutually orthogonal. So, they are orthogonal, not necessarily orthonormal, but it will be like this. A times alpha 1 1, just as an example, A times alpha 1 1 will be sigma 1 beta 1 1. So, sigma 1 0 0 0. A times alpha 1 n 1, alpha 1 n 1 will be again sigma 1 beta 1 n 1. Okay. So, sigma 1 will continue for a while. How many times? N 1 times. Okay. Similarly, dot dot dot, after a while sigma r will continue n 1 n r times and then zeros. So, it is a diagonal matrix where there will be non-zero, there will be positive, strictly positive diagonal entries consisting of the singular values and then zeros. Okay. You can call it say D. Now, since this matrix I called sigma, this matrix you can call say capital gamma, So, in short, using short notation, A times sigma is gamma times D, or A is, since sigma is, I mean all the columns are mutually orthogonal, rather orthonormal, sigma transpose sigma, sigma is unitary, sigma transpose sigma will be identity, that is sigma transpose itself is sigma inverse. If I post multiply it by sigma transpose, it will become identity, and here. So, that means gamma D sigma transpose. This is called SVD of A, and D consists of the D consists of the singular values. To get the singular values is not very difficult. Given an A, you just form A transpose A or A transpose and take the eigen values, whichever is the non-zero eigen values, you find out total number of such non-zero eigen values including their multiplicity. Okay. Those non-zero eigen values will form their this thing, they will be called the singular values. In fact, in many signal processing work, these non-zero signal values, these non-zero positive singular values, they actually come from signal, and in a signal plus noise situation, those singular values which are not 0, but very small, they can be detected as coming from noise. Actually, those problems exist, you will see, and those are called subspace based signal estimation techniques, and all this entire thing rests on this SVD thing. Okay. Another thing is, that suppose A is a matrix and in general is a rectangular matrix, you are asked to find out the rank of A, but we know that rank of A is same as rank of A transpose A. And what is rank of A transpose A? Number of, that is, if you have to find out the range space, and range space is given by what? The that is this is the range space. So, dimension of this will be the rank, okay, of A transpose A. And what is the dimension? First we find out multiplicity of lambda 1, then multiplicity of lambda 2 dot 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 multiplicity of lambda r. That is, what are those eigenvalues? Non-zero eigenvalues. Find out their multiplicities, add, that will be the rank. So, simply to find out the rank of A, you need to find out the singular values A transpose, that is the eigenvalues of A transpose A, find out the non-zero eigenvalues, just add their respective multiplicity, that will be the rank. Okay. So, that is how SVD is used for rank determination. There are other applications of SVD, but before I go, before I mention them, maybe I consider this proof, because this is something I assumed throughout this course and did not prove. So, I assume I now prove the diagonalizability of Hermitian matrices, but time being short, I might run through it. So, suppose you are given a matrix A, and now I will make A to be Hermitian and in general complex to make it more general. Okay. So, C may be n cross n, A Hermitian is A, that is A is Hermitian matrix. Okay. Now, form A V 1 as lambda 1 V 1, that is I form is find out its I try to find out its eigenvalues and eigenvector. I get at least one eigenvector, say call it V 1, that is V 1 not equal to 0 eigenvector. Okay. And not only that, you normalize the eigenvector, so that its norm is 1. Okay. That is, we find out this. Then by this I denote space spanned by V 1 vector, and by its orthogonal complement I did spanned by, it is what? Subspace of C n, the space which is orthogonal to this. And what will be the basis of this? That is, if you take V 1 and then consider this space and by Gram-Schmidt orthogonalization get n minus 1 orthogonal basis vectors, okay, then consider those n minus 1 orthogonal basis vectors and take their span, that span will be this. This is all the standard stuff, this we have done. So, I will not spend too much time on this, and in this case the total vector space C n can be written as a direct sum, rather I would say orthogonal sum of, because one is the orthogonal of other. And now you consider V element of this. This means, if I take, then I will show that if you take V element of this, on that you apply A matrix, that is A V, A V also will belong to this. That is this subspace V 1 orthogonal V 1, I mean this orthogonal, this subspace, that is complement of orthogonal complement of the span of V 1, that is invariant under A, that is any vector picked from the subspace, on that if you apply A, you get back something from there. That is very easy. That is, if you take A V, if you take the inner product between say this given V 1 and A V, what you get is V 1 H A V, but A and A H are same. So, I can write it as V 1 H A H V. This means V H A V 1 whole together H, and A V 1 we know is lambda 1 V 1. So, lambda 1 V H V 1 H, but because of orthogonality this is equal to 0, because V 1 belongs to this space spanned by V 1 and V is taken from its orthogonal complement. So, this is 0. So, that means, if V belongs to this, that is V belongs to the space which is orthogonal to span of V 1, then A V also belongs there, because inner product between A V and that mother vector V 1, this is 0. Okay. This we have seen. Now, suppose I form, we are already given V 1 and by this Gram-Schmidt orthogonalization, that could be one of the method. I form other vectors V 2 dot 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 V n, okay, where this part, this is orthonormal say, and this span this part, it span, okay, obviously orthogonal. This is an orthogonal basis, orthonormal basis of C n. Okay. You give me V 1, then by Gram-Schmidt orthogonalization I form the other orthogonal vectors V 2 to V n. Okay. And if I consider the V 2 to V n only, they only span this space, that is very trivial to see. Okay. This is the case. This V 2 to V n, I form a submatrix A V 2 dot 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 V n. That means, what is A? A is not A, and then I form one matrix U 1 as V 1 and W. Clearly, this is a unitary matrix, because all the elements of this matrix, all the columns are mutually orthonormal. Okay. That means, U 1 Hermitian, if you take U 1 Hermitian U 1, you will get identity, that is obvious, because the columns are mutually orthonormal. This is given to me. Now, if I consider U 1 Hermitian A U 1, okay. You remember, when you diagonalize a matrix, this is what we get. I mean, on unitary matrix it is Hermitian times the given matrix times the original one, and that results in a diagonal matrix. So, suppose, I am going in that direction. So, I formed a unitary matrix using this basis, okay, and then consider its Hermitian U 1 Hermitian, then multiplied by a U 1. Is it diagonal? Answer is no, it will not be diagonal so easily, but we are going one step in that direction. What happens to this matrix if you really write this way? This is actually V 1 Hermitian. If you take U 1 Hermitian, first column becomes first row with Hermitian with conjugate transpose. So, this is the thing A, and this is V 1 W. So, this is U 1 Hermitian A, and then if you do elementary matrix multiplication, you will see this result V 1 Hermitian A V 1, V 1 Hermitian A W, W Hermitian A V 1 and W Hermitian A W, out of which very quickly A V 1 is lambda 1 V 1. So, lambda 1 goes out, V 1 Hermitian V 1, V 1 is unit norm. So, that is 1. So, first element is lambda 1. A V 1, that is again lambda V 1, lambda goes out, lambda 1 V 1, lambda goes out, W Hermitian V 1 will be 0, because V 1 is orthogonal to all the elements of all the columns of W. So, this becomes a 0 Hermitian, that is a column vector Hermitian, or you can put a transpose, because it consists of only zeros. On this side A W. Okay. Now, I told you that any vector if you pick up from, I mean from V 2 to V n, they all belong to this orthogonal complement, and if you pick up any vector from there, say V 2 to V n, apply A over that, that also remains there, which means inner product between that and V 1 will be 0. That is V 1 is orthogonal to A W, all the columns of A W, because A W is nothing but A V 2, A V 3, A V 4 dot dot dot, and A V 2, A V 3, they are all belonging to this orthogonal complement that we have proved just a while back, and therefore, their inner product with V 1 will be 0. So, I get a again here, in fact, I should write just 0 vector, it's a column vector is my notation, this should be 0 Hermitian, and this one A W. Now, question is, this is again Hermitian, you can call it A prime, you can easily see it is Hermitian, that is A prime. If you take A prime Hermitian, you get A prime, that is because of the structure. You take the Hermitian, W Hermitian comes first, A Hermitian, A Hermitian is same as A, and this W H goes to the end and becomes W, you get by the original one, it is A. This is Hermitian. So, that means this becomes so, but since now we concentrate on this A prime, whatever we have done so far, okay, the same approach we can apply on this A prime, but this time it is the vector space is C n minus 1, because dimension of this matrix is n minus 1 cross n minus 1. So, that means we can construct again some u 1 prime, we can construct some u 2 prime, okay, in the same way for this Hermitian matrix, we can consider in the same way, but they are all dimension n minus 1. Okay, if it is a vector, length is n minus 1, if it is a matrix n minus 1 cross n minus 1. So, u 2 prime, so that u 2 prime A prime, u 2 prime is again taking up this kind of structure, some eigenvalue lambda 2, 0, 0 Hermitian, and then another Hermitian matrix, say A double prime Hermitian. Okay. So, now if I define u 2 as simply 1, 0, 0 Hermitian and this u 2 prime, then again it becomes n cross n, because our problem was that one matrix u 1 is n cross n, this is n minus 1 cross n minus 1. So, there is a problem in connecting these matrices, size was, there was an incompatibility. So, I just put that u 2 prime as a sub matrix of a bigger matrix, okay, just added 1 here and zeros and zeros, u 2. U 2 is Hermitian, you can see, u 2 is u 2 is unitary, you can easily see. This addition of 1 and then 0 and 0, it does not change unitariness, because u 2 prime was unitary. That is how it took, u 2 prime for this Hermitian matrix was unitary. You can easily see that u 2 H, u 2 is identity, okay, which is also u 2 H, this easily, you know. So, therefore, if you consider now this case u 2 Hermitian, u 1 Hermitian, A u 1 u 2, originally you had this, that gave you this matrix, and again applying the structure with 1 here and 0 and 0 and u 2 prime, if you put that back here, you will see, I will not do this elementary matrix multiplication results, you will see first you will have lambda 1, lambda 2, then zeros, zeros, here is a 0, zeros, here also zeros, and then there is another matrix, okay, that is that A double. So, you see by progressive, and this is again Hermitian. So, by going progressive doing it again and again and again, the entire matrix gets diagonal, and u 2, remember I get u 1 u 2 here, this is a unitary matrix, okay, but product of two unitary matrix makes it a unitary matrix. So, in general I will get in the end I will get a product like, you know, I mean u1, u2 dot 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 up to un. Okay, n number of unitary matrices. This product you can call U. This will be unitary, which means you will have a situation like this U Hermitian, like here. If this is U, this is a Hermitian of that. U Hermitian, originally U will be nothing but all the eigenvalues lambda 1, lambda 2 up to say lambda something, lambda n. They may be distinct or they may be repeated. This I am not bothered. Okay. So, therefore, you can take this U, you can take this UH on this side, you can make it even A U as, if you multiply by U on this side, UH is 1. So, here also U and the same matrix. Then you can easily see that if the columns of you take the columns of U, they are mutually orthonormal, and A times each column is 1 lambda times the corresponding column. So, they correspond to eigenvectors. Okay. So, those eigenvectors you can easily see they are and how many, as many as the dimension of n, that is n. So, the matrix is diagonalizable, which also means here that I get totally n mutually orthogonal basis vectors. Some of them can correspond to the eigen subspace of lambda 1 if it is repeated, some could correspond to the eigen subspace of lambda 2, so on dot 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 dot, but they are mutually orthogonal and is diagonalizable. So, this shows that a Hermitian matrix is diagonalizable. Okay. So, it completes the proof. Some SVD applications, there are many, unfortunately, I cannot get into them, but one thing you see, we have done this least squares minimization thing. There is, suppose there is a data matrix given, okay, say A, say data matrix given, I do not know what notation was used, A n, it consists of the data vectors x 1 n starting from 0 to n, x 2 n dot dot dot, say x r n, and there is a desired response vector d 0 dot 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 d n. We have done the least squares minimization, and that time we tried to say that find out coefficients of vector c as c 1 dot 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 c r, that is as many as the number of columns here, so that d n minus a n c its norm square is minimized. And we got that I mean we connected this to orthogonal projection problem and all that, and since orthogonal projection is unique. Okay. I mean we get one such, I mean a unique projection exists, and we got that equation as A transpose n A n times C, C opt was A transpose n d n. Then if the columns, that time we assume that the columns are linearly independent and it is full rank. Okay, it is full rank, and therefore, we could easily, I mean if it is full rank, then A transpose A n also will have will be strictly positive definite. Okay, if the columns are not, it is positive definite and therefore invertible. So, you take it on this side. That time we said that A transpose n A n inverse A transpose n d n, and this part I called pseudo inverse of A n. But suppose A transpose A n is such the columns are not linearly independent, then you cannot invert it, which means you got a matrix here which is rank deficient, and therefore, this equation has more than one solution. Projection will be same, because whichever solution you put here A n c will be same, A n times c will be same, but solutions are many. In this case, SVD can be used to find out a solution which has the minimum norm of C opt. That is, there are many solutions possible. If you apply SVD here, then you get the solution that takes the minimum norm. Okay, this is a very vital application of SVD. Another is that suppose given a matrix of rank deficient square matrix, okay, and you want to approximate it to given a square matrix of some rank, maybe full rank, but you want to approximate it to a lower rank matrix, then the best such approximation can be also obtained by SVD. There are many algorithms to compute SVD and all. SVD has got tremendous applications in signal processing, control and communication. My purpose was to introduce this topic as an appendix to you people, okay, and also through that process do this bit of linear algebra, which I did not do in this course. So, at least Linear algebra wise, this course is kind of complete, you can say. We tried to cover a lot. Okay. So, that is all for this course, and if you have any feedback on it, you can communicate to me later. Thank you very much.